Imagine volunteering for a mission knowing you'll never breathe unfiltered air again. Never feel rain, never hug someone you left behind. Now imagine NASA doesn't explicitly tell you it's a one-way trip, but the physics, the biology, and the math all point to the same conclusion. You're not coming home. This is the hidden reality of Mars missions, and it changes everything. If you're fascinated by the mysteries of space exploration, hit that subscribe button and give this video a like. It helps me bring you more content about the wonders and challenges of exploring the cosmos. Now let's get started. Let's talk about what makes Mars so deceptively difficult. When you look at Mars through a telescope, it doesn't seem that far away. It's right there, a reddish dot in the night sky, sometimes visible to the naked eye. Ancient civilizations saw it and named it after their gods of war. In the late 1800s, astronomers like Percival Lowell thought they saw canals on its surface, evidence of an advanced civilization struggling to survive on a dying world. We know now those canals were optical illusions, tricks of light and atmosphere, and wishful thinking, but the dream of Mars persisted. In 1965, Mariner 4 became the first spacecraft to successfully fly by Mars and send back images. What it revealed shocked the world. Not canals, not cities, not vegetation, just craters. A dead, cold desert that looked more like the moon than the living world people had imagined. It was a devastating blow to the romantic vision of Mars. But it didn't kill the dream. If anything, it transformed it. If Mars was dead, maybe we could bring it back to life. If it was empty, maybe we could fill it. If it was a blank canvas, maybe we could paint something new there. The modern era of Mars exploration began in earnest in the 1990s. Mars Pathfinder landed in 1997 with its little rover Sojourner, no bigger than a microwave oven, trundling across the Martian surface and capturing the imagination of millions. Then came the giants, Spirit and Opportunity in 2004, Curiosity in 2012, Perseverance in 2021. Each mission revealed more about Mars, peeling back layers of mystery. We found evidence of ancient rivers and lakes. We discovered organic molecules. We detected seasonal methane releases that might, just might, indicate microbial life beneath the surface. And with each discovery, the calls grew louder. Send humans. Stop exploring Mars with robots and start exploring it with people. Let humans walk on Martian soil, drill into Martian rocks, search for Martian life with their own eyes and hands. The vision became irresistible. Mars wasn't just a destination anymore. It was humanity's backup plan, our insurance policy against extinction, the next step in our evolution from a single-planet species to a civilization among the stars. But here's where reality intrudes on the dream. Because getting to Mars is one thing. Getting back is something else entirely. And the difference between those two things is where our story really begins. Let's start with the most obvious problem: distance. Mars orbits the Sun at an average distance of about 228 million kilometers. Earth orbits at about 150 million kilometers. But planets don't stay in one place. They're constantly moving, orbiting the Sun at different speeds. Earth completes its orbit in 365 days. Mars takes 687 days. This means the distance between Earth and Mars is constantly changing. At their closest approach, called opposition, Earth and Mars are about 55 million kilometers apart. At their farthest, when they're on opposite sides of the Sun, they're about 400 million kilometers apart. That's more than 7 times farther. So if you want to send a mission to Mars, you don't just aim at where Mars is now. You aim at where Mars will be when your spacecraft arrives. It's like throwing a ball to someone who's running, except you're both on different moving walkways that are also rotating, and the whole thing is happening in 3 dimensions across millions of kilometers. The optimal launch window. When Earth and Mars are positioned just right for the most fuel-efficient transfer, only comes around every 26 months. Miss that window, and you wait another 2 years. This already creates a problem for round trips. If you launch humans to Mars during one window, they arrive roughly 6 to 9 months later, depending on the exact trajectory. But now Mars and Earth are in different positions. The return window doesn't open for another 1.5 to 2 years. So right there, you have your first constraint. Any human mission to Mars must be prepared to stay for at least 1.5 years, just waiting for the planets to align correctly for the return journey. That's not a quick visit. That's not boots on the ground for a few weeks and then home. That's a minimum 18-month stay, probably longer to make the trip worthwhile. You're looking at a total mission duration of at least 2.5 to 3 years from launch to return. Now, 3 years doesn't sound impossible. The International Space Station has been continuously occupied since November 2, 2000. Astronauts have spent up to nearly a year in space. Russian cosmonaut Valery Polyakov spent 437 consecutive days aboard the Mir space station in the mid-90s. Humans can survive extended periods in space. We know this, but here's the critical difference. The ISS orbits just 400 kilometers above Earth's surface. If something goes catastrophically wrong, astronauts can evacuate and be back on Earth within hours. Mars is months away. There's no quick abort. There's no emergency return. You're committed. And that brings us to our first major reason why Mars might be a one-way trip: the biological toll of long-duration spaceflight. When you leave Earth's protective embrace, your body begins to change in ways that are profoundly troubling. Some of these changes are reversible. Some might not be. Let's start with your bones. On Earth, your skeleton constantly rebuilds itself, maintaining its density and strength against the pull of gravity. In microgravity, that stimulus disappears. Your body, being ruthlessly efficient, decides it doesn't need all that heavy bone tissue anymore, so it starts breaking down bone faster than it builds it back up. Astronauts on the ISS lose about 1 to 2% of their bone mass per month. That might not sound like much, but over a 3-year Mars mission, you're looking at potential bone loss of 30 to 70% in critical areas like the hips and spine. That level of bone loss puts you at risk for fractures from activities that would be trivial on Earth. Imagine surviving the journey to Mars, spending 18 months exploring the red planet, making it back to Earth orbit, and then breaking your hip when you try to stand up in Earth's gravity. It sounds absurd, but it's a real concern. Astronauts returning from the ISS after 6 months need to be carried out of their capsules. They can't walk. Their bodies have adapted to weightlessness, and Earth feels impossibly heavy. Now imagine that effect multiplied several times over. Some researchers believe there might be a point of no return, a threshold beyond which bone loss becomes irreversible. Your skeleton might never fully recover. You might be permanently disabled by Earth's gravity, even though you're perfectly functional in the reduced gravity of Mars or in weightlessness. You would become adapted to space in a way that makes Earth uninhabitable for you. Then there's your muscles. Like your bones, your muscles atrophy in microgravity. On Earth, you use your muscles constantly just to stand, to walk, to sit upright against gravity's pull. In space, that constant workout disappears. Astronauts on the ISS exercise for about 2 hours every day using specialized equipment, and they still lose significant muscle mass. On a Mars mission, you'd need to exercise religiously during the months-long journey there and back. But even with perfect adherence to an exercise regimen, muscle loss is inevitable. Your heart is a muscle too, and it's not immune to these changes. In microgravity, your heart doesn't have to work as hard to pump blood throughout your body. It becomes weaker, smaller. The cardiovascular deconditioning is so severe that astronauts returning from space often experience orthostatic intolerance, which is a fancy way of saying they get dizzy and faint when they stand up because their hearts can't efficiently pump blood to their brains against gravity. But bones and muscles, as concerning as their deterioration is, might be the least of your problems, because there's something far more insidious waiting for you in deep space: radiation. On Earth, we're protected by 2 shields that we barely think about. The first is Earth's magnetic field. a bubble of magnetism generated by the churning molten iron in our planet's core. This magnetosphere deflects most of the charged particles streaming from the sun, the solar wind that would otherwise strip away our atmosphere and bombard the surface. The second shield is the atmosphere itself, a 100-kilometer thick blanket of air that absorbs and scatters radiation. In low Earth orbit, where the ISS lives, you still have significant protection from both these shields. Astronauts receive about 50 to 200 millisieverts of radiation during a 6-month stay on the station. That sounds like a lot, and it is. It's roughly equivalent to getting full-body CT scans every few weeks. But it's manageable. It increases cancer risk, but not catastrophically. Mars missions are a different story entirely. Once you leave Earth's magnetosphere, you're exposed to the full fury of cosmic radiation. There are two main types you need to worry about. The first is solar particle events, massive eruptions from the sun that send waves of high-energy protons racing through space. These events are unpredictable and can deliver lethal doses of radiation in hours if you're caught unshielded. The second is galactic cosmic rays, particles accelerated to near light speed by supernovae and other violent events across the galaxy. These particles are so energetic they can tear through spacecraft hulls, through water, through your body, shredding DNA and killing cells. Current estimates suggest that astronauts on a Mars mission would receive somewhere between 600 to 1,000 millisieverts of radiation during the round trip, possibly more. That's approaching the career limit that space agencies set for astronauts. One mission to Mars could give you a 5 to 10% increased lifetime risk of fatal cancer, and that's assuming an average mission during a relatively quiet period of solar activity. But the cancer risk, as terrifying as it is, might not be the worst effect. There's growing evidence that cosmic radiation causes cognitive damage. Studies on mice exposed to radiation, similar to what astronauts would experience in deep space, show troubling results. Impaired memory, reduced ability to learn new tasks, increased anxiety, degraded decision-making. The particles don't just damage cells, they cause inflammation in the brain that persists long after exposure. Imagine sending astronauts to Mars only to have them return with permanent cognitive impairment. Imagine them making critical errors during the mission because their brains have been damaged by months of radiation exposure. This isn't science fiction speculation. This is data from actual experiments, and it's one of the most serious concerns facing long-duration spaceflight, and we haven't even talked about what happens when you actually get to Mars. Because Mars, despite being the most Earth-like planet in our solar system, is fundamentally hostile to human life in ways that are easy to underestimate. Let's start with the atmosphere, or rather the lack of one. Mars has an atmosphere that's less than 1% the density of Earth's at sea level. It's so thin that it provides almost no protection from radiation and almost no insulation from temperature extremes. The average temperature on Mars is around minus 63 degrees Celsius, but it varies wildly. At the equator during summer, daytime temperatures can reach an almost comfortable 20 degrees Celsius, but at night, they plunge to minus 73 degrees Celsius. At the poles in winter, temperatures drop to minus 125 degrees Celsius. You can't breathe the atmosphere. It's 95% carbon dioxide with trace amounts of nitrogen and argon. There's essentially no oxygen. Step outside without a pressure suit, and several things happen simultaneously, none of them good. The low pressure causes the liquids in your body to vaporize. Your blood doesn't boil in the Hollywood sense, but the water in your soft tissues starts forming bubbles. You'd swell up like a balloon. The lack of oxygen would make you lose consciousness in about 15 seconds. You'd die within a minute or two. So you need a spacesuit every time you go outside. Not the relatively lightweight suits astronauts wear on the ISS for spacewalks, but heavy-duty surface suits that can handle Martian dust, temperature extremes, and the constant low pressure. These suits need to be reliable for hundreds of hours of use because you'll be wearing them constantly. Any failure, any tear, any malfunction in the life support, and you die. The Martian surface is covered in dust. Not the friendly dust bunnies under your bed, but microscopic particles of iron oxide and other minerals that are electrostatically charged by the thin atmosphere and low humidity. This dust sticks to everything. It's abrasive like powdered glass. It gets into seals, into mechanical joints, into airlocks. During the Apollo missions to the Moon, lunar dust was one of the most persistent problems. It clogged equipment, abraded surfaces, and even caused respiratory irritation when astronauts brought it back into their habitat on their suits. Martian dust would be worse because you'd be dealing with it not for days, but for months or years. Then there's the gravity, or more accurately, the lack of sufficient gravity. Mars has about 38% of Earth's gravitational pull. That's better than the zero gravity you experience during the journey there, but it's still not enough to prevent many of the physiological changes we talked about earlier. Your bones and muscles will continue to deteriorate on Mars, just more slowly than in weightlessness. After 18 months on Mars, followed by another 6 to 9 months in zero gravity on the return journey, your body might be so deconditioned that Earth's gravity becomes genuinely dangerous to you. There's also the psychological dimension, which is harder to quantify but equally important. You're living in a confined habitat, millions of kilometers from home, with the same handful of people for years. There's no fresh air, no rain, no seasons in the way you're used to experiencing them. Every time you go outside, you're surrounded by a landscape that, while scientifically fascinating, is utterly dead. No birds, no insects, no plants, no wind-blown trees or flowing water. Just rust-colored rocks and dust stretching to the horizon under a butterscotch sky. The psychological studies of Antarctic research stations and submarine crews give us some insight into what this might be like. Even in those environments, which are paradise compared to Mars, you see increased rates of depression, anxiety, interpersonal conflict, and cognitive decline. Now imagine that same isolation but with the added stress of knowing that any major system failure means certain death, that there's no rescue coming, that the entire planet is actively trying to kill you every moment you're there. Some of the astronauts who've spent the longest periods in space talk about the overview effect, a cognitive shift that happens when you see Earth from space, a profound realization of how fragile and precious our planet is. But there's also a darker side that some experience, a feeling of alienation, of no longer quite belonging to Earth, of being changed in fundamental ways by the experience. On a Mars mission, that alienation would be amplified beyond anything we've experienced before. Now let's talk about the logistics of actually getting back from Mars, because this is where the one-way nature of the trip becomes truly apparent. To leave Mars and return to Earth, you need a fully fueled rocket sitting on the Martian surface, ready to go. That rocket needs to be powerful enough to lift off from Mars, achieve escape velocity, and send a capsule on a trajectory back to Earth. We're talking about a vehicle roughly equivalent to the upper stages of a Saturn V rocket, the monster that sent astronauts to the Moon. Here's the problem. You can't bring that rocket fully fueled from Earth. The amount of fuel needed is staggering. If you tried to launch a Mars mission with enough fuel for both the journey there and the return journey, plus the fuel to land on Mars and take off again, your spacecraft would be impossibly massive. The rocket equation, that cruel mathematical reality that governs all spaceflight, works against you. Every kilogram of fuel you want to use at the end of your journey requires you to carry it along the entire way, which means you need more fuel to carry that fuel, which means you need even more fuel to carry that fuel, and so on in a vicious exponential spiral. The only realistic solution is to manufacture the return fuel on Mars using local resources. This process is called in situ resource utilization, or ISRU. The basic idea is this: you send equipment to Mars ahead of the human mission. This equipment lands on Mars, scoops up Martian regolith, or extracts water ice from beneath the surface, and uses solar or nuclear power to split water into hydrogen and oxygen, or to combine carbon dioxide from the atmosphere with hydrogen to create methane and oxygen. These propellants are stored in tanks attached to your return vehicle. By the time humans arrive, the return rocket is fueled and ready. SpaceX's Starship design, which Elon Musk envisions as the vehicle that will take humans to Mars, relies heavily on this concept. The plan is to use the Sabatier reaction, combining carbon dioxide from Mars's atmosphere with hydrogen brought from Earth or extracted from Martian water to produce methane fuel and oxygen. It's elegant in theory. The chemistry is well understood. We've done it in laboratories here on Earth. But doing it on Mars, with equipment that has to function autonomously for months or years in one of the harshest environments in the solar system, is another matter entirely. What if the fuel production system fails? What if it produces fuel more slowly than expected? What if contamination from Martian dust degrades the equipment? What if there's a design flaw that only becomes apparent after the system has been running for months? If the fuel production fails, the astronauts on Mars are stranded. There's no backup. There's no plan B. Earth can't send a rescue mission because, remember, the launch windows only align every 26 months, and it takes 6 to 9 months to get there. By the time a rescue mission could arrive, the stranded astronauts would have been on Mars for 3 to 4 years, far beyond the planned mission duration, likely beyond their consumable supplies. You might think, well, just send extra supplies. Send enough food, water, and oxygen for 5 years instead of 3, just in case. But every kilogram of supplies you send increases the mass of your mission, which requires more fuel to launch from Earth, which makes everything more expensive and more complex. There are hard practical limits to how much margin you can build into the mission. And even if the fuel production works perfectly, you still have to worry about the return vehicle itself. It's been sitting on Mars for potentially 2 years, exposed to temperature swings of 100 degrees Celsius every day, to dust storms, to cosmic radiation. Will the electronics still function? Will the seals and gaskets remain intact? Will the engines fire reliably? On Earth, we don't leave rockets sitting fueled on the pad for months, let alone years, because propellants are corrosive and components degrade. On Mars, you don't have a choice. Let's say everything works. The fuel production succeeded. The return vehicle is functional. The crew boards the ascent vehicle and launches from Mars. Now they face another 6 to 9 months in deep space, during which they accumulate more radiation exposure, more bone loss, more muscle atrophy, more cognitive decline. They're already compromised from the outbound journey and the Mars surface stay. Now they're being pushed even further beyond normal human limits. When they finally approach Earth, they face one of the most dangerous parts of the entire mission: re-entry. You're traveling at about 11 kilometers per second relative to Earth. You have to hit the atmosphere at precisely the right angle. Too steep, and the deceleration forces will kill you or burn up your capsule. Too shallow, and you'll skip off the atmosphere like a stone skipping on water, bouncing back into space with no way to slow down. The margin for error is razor thin. The Apollo astronauts returning from the Moon experienced re-entry velocities of about 11 kilometers per second. They described seeing their capsule window glow orange, then white-hot as the heat shield ablated away, temperatures outside reaching nearly 3,000 degrees Celsius. The G-forces peaked at about 6 Gs, 6 times Earth's normal gravity pressing them into their seats. For young, healthy, fit astronauts who'd only been in space for a week or so, it was brutal but survivable. Now imagine going through that same experience after 3 years in space. Your bones are fragile, your muscles are wasted, your cardiovascular system is deconditioned. Your body has spent years adapting to low gravity and weightlessness, and now suddenly you're being subjected to 6 times Earth's gravity. The risk of medical emergencies during re-entry, broken bones, cardiovascular collapse, stroke, is significant. And if you survive re-entry, you face months of painful, difficult rehabilitation. Astronauts returning from 6-month ISS missions describe the first weeks back on Earth as agonizing. Everything hurts. Standing is exhausting. Walking feels like climbing a mountain. Your balance is destroyed because your inner ear has adapted to weightlessness. Some astronauts need wheelchairs for the first few days. Most need assistance with basic tasks for weeks. Scale that up to a 3-year mission, and you're looking at potential disability that might last months or years. Some astronauts might never fully recover. They might have permanent cardiovascular problems, permanent bone density loss that leaves them prone to fractures, permanent changes in vision from the fluid shifts that happen in zero gravity. In a very real sense, they wouldn't be the same people who left Earth. They would be fundamentally changed, adapted to space in ways that make them less suited for life on their home planet. This brings us to a profound question that space agencies don't like to discuss publicly. At what point does a return mission become meaningless? If the astronauts who return from Mars are so physically compromised that they'll never live normal lives on Earth again, have they really returned? Or have they simply relocated their suffering from Mars to Earth? Some researchers have started asking whether it might actually be more humane to plan for one-way missions from the start. If we're honest about the fact that Mars explorers might be permanently disabled by the journey, might never fully readapt to Earth, might face dramatically shortened lifespans from radiation exposure, then perhaps we should stop pretending we're sending them on round trips. Perhaps we should select people who understand and accept that they're saying goodbye to Earth forever. This isn't as radical as it sounds. Throughout human history, explorers have embarked on journeys knowing they'd likely never return. The Polynesians who sailed across the Pacific to settle remote islands, the colonists who traveled from Europe to the Americas, the pioneers who crossed the American continent in covered wagons. Many of them died on the journey. Most knew they'd never see their homelands again. Yet they went anyway, driven by curiosity, by the desire for a new life, by the fundamental human urge to see what's over the next horizon. In 2012, a Dutch organization called Mars One announced plans to send humans on a one-way mission to Mars, establishing a permanent colony with no return option. The project was heavily criticized and ultimately failed due to financial and technical problems, but the announcement drew over 200,000 applications from people willing to leave Earth forever. 200,000 people looked at the prospect of dying on Mars and said yes. What does that tell us about human nature? Are these people suicidal, reckless, irresponsible? Or are they the same kind of people who've always pushed humanity forward, the ones willing to sacrifice personal safety for the chance to be part of something larger than themselves? There's also a compelling economic argument for one-way missions. If you eliminate the need to bring astronauts back, you dramatically reduce mission complexity and cost. You don't need fuel production on Mars. You don't need a return vehicle. You don't need to plan for a 3-year mission timeline. You can send people during any launch window because you're not worried about return windows. The mission becomes simpler, cheaper, and arguably safer because you're eliminating many of the most dangerous and uncertain elements. The astronauts would need supplies, of course. They'd need continuous shipments of food, spare parts, medical supplies. But these cargo missions don't have the same constraints as crewed missions. They can take slower, more fuel-efficient trajectories. They don't need life support systems or radiation shielding for humans. You could send several cargo ships for the cost of one crewed return mission. And here's the thing. If you're planning to actually colonize Mars rather than just visit it, eventually you need people who will stay. You need people willing to live out their lives on Mars, to build infrastructure, to conduct long-term research, to establish a permanent human presence. The first Mars missions, whether we acknowledge it or not, are essentially one-way trips for the species. We're not going to Mars and then abandoning it. We're going and staying. But let's confront the ethical nightmare at the heart of this idea. How do you get informed consent from someone volunteering for a one-way mission to Mars? How can anyone truly understand what they're agreeing to? You can show them simulations, put them through training, have them talk to astronauts who've been in space. But none of that captures the reality of knowing you'll never breathe unfiltered air again, never feel rain on your face, never swim in an ocean, never hug a friend you left behind on Earth. And what about the psychological impact of that finality? It's one thing to go on a 3-year mission knowing you're coming home. It's entirely different to leave knowing you'll die on Mars. Some psychologists argue that humans need hope, need something to look forward to, and that taking away the possibility of return removes an essential psychological anchor. Others counter that humans are remarkably adaptable, that we find meaning and purpose wherever we are, and that the pioneers who settle Mars would create new lives, new communities, new reasons to live. There's also the question of what happens when things go wrong, and in space exploration, things always go wrong. Apollo 13 is the famous example. An oxygen tank exploded halfway to the moon, and the mission became a desperate struggle for survival. The astronauts made it home through a combination of skill, ingenuity, and sheer luck. But they had one crucial advantage. They were only a few days from Earth. Mission Control could communicate with them in real time, troubleshoot problems, devise solutions. On Mars, communication delay is between 3 and 22 minutes one way, depending on where Earth and Mars are in their orbits. If something goes catastrophically wrong, the astronauts are on their own. They can't call for help. By the time their distress signal reaches Earth and a response comes back, they might already be dead. And even if ground control comes up with a solution, there's no guarantee the astronauts will have the equipment, the supplies, or the time to implement it. In 2003, the Space Shuttle Columbia broke apart during re-entry, killing all 7 astronauts aboard. The investigation revealed that a piece of foam insulation had struck the shuttle's wing during launch, damaging the heat shield. The astronauts had no idea anything was wrong. They were doomed from the moment they launched, but they didn't know it. If that same kind of catastrophic but non-obvious damage happened to a Mars mission during launch or on the way there, the crew might not realize they were already dead until they tried to come home and their spacecraft failed during the return journey. This raises a grim question. Would it be better to die quickly on Mars from an obvious accident, or to die slowly realizing that your return vehicle is damaged beyond repair and you're going to run out of consumables before help can possibly arrive? In a one-way mission scenario, at least that second nightmare is off the table. You're not coming back anyway. Equipment failures become problems to solve rather than death sentences. Now let's talk about something that doesn't get discussed enough in conversations about Mars missions: the biological contamination question. This cuts both ways, and both directions are concerning. First, there's the question of forward contamination, meaning bringing Earth life to Mars. Despite our best sterilization efforts, spacecraft are never truly sterile. They carry microbes from Earth, hardy bacteria that can survive in extreme conditions. Some of these organisms might be able to survive or even reproduce in Martian environments, especially if they find their way into subsurface water or ice deposits. Why does this matter? Because if there's life on Mars, native Martian microorganisms that evolved independently from Earth life, contamination from Earth could destroy it before we even know it exists. Imagine finally finding evidence of alien life, only to realize we killed it by introducing competing Earth organisms. It would be one of the greatest tragedies in the history of science, and if humans go to Mars, especially if they stay there permanently, preventing forward contamination becomes essentially impossible. Humans are walking biomes. We're covered in and filled with trillions of microorganisms. We shed skin cells constantly. We exhale bacteria with every breath. A permanent human presence on Mars means contaminating Mars with Earth life. There's no way around it. Then there's backward contamination, the possibility of bringing Martian life or Martian materials back to Earth. This was a serious concern during the Apollo program. When the first astronauts returned from the moon, they were quarantined for weeks in case they'd been exposed to lunar pathogens. We know now the moon is sterile, but we didn't know then. Mars is different. Mars might have life. Probably not complex life, but potentially microorganisms adapted to Martian conditions in ways we can't predict. What if Martian microbes are biochemically compatible enough with Earth life to infect terrestrial organisms, but our immune systems have no defenses against them because they're fundamentally alien? It sounds like science fiction, like the Andromeda strain, but it's a legitimate concern that planetary protection officers at NASA and other space agencies take seriously. The probability might be low, but the consequences could be catastrophic. A one-way mission to Mars eliminates the backward contamination risk entirely. If the astronauts never come back, if all the samples they collect stay on Mars, then Earth remains protected. You could argue that from a planetary protection standpoint, one-way missions are actually more responsible than round-trip missions. Of course, this assumes we're okay with potentially sacrificing the astronauts if they do encounter dangerous Martian pathogens, which raises a whole other set of ethical questions. Let's shift gears and talk about something more practical: water. Humans need water to survive, about 2 to 3 liters per day for drinking, plus additional water for food preparation, hygiene, and growing plants. Over a year, one person needs roughly 1,000 liters of water just for drinking. For a crew of 4 on an 18-month Mars surface mission, that's over 7,000 liters just for basic hydration, not counting water for other purposes. You can't bring that much water from Earth. It's too heavy. A liter of water weighs a kilogram, so 7,000 liters is 7,000 kilograms, or 7 metric tons, just for drinking water. Instead, you need to either recycle water with incredible efficiency or extract it from Mars itself. The International Space Station recycles about 93% of all water, including condensation from breath and sweat and urine. Yes, astronauts drink recycled urine. The technology works, but it requires constant maintenance and occasionally fails. On Mars, water recycling would be even more critical because resupply missions would be infrequent and expensive. You'd need to achieve near-perfect recycling efficiency. Any losses would need to be made up by extracting water from Martian sources. We know there's water ice on Mars, lots of it, particularly near the poles and in the mid-latitudes just beneath the surface. The Phoenix lander in 2008 confirmed this directly by digging trenches and observing ice. The Mars Reconnaissance Orbiter has identified numerous locations where subsurface ice is accessible. But extracting that ice, melting it, purifying it, and bringing it into your habitat is a major engineering challenge. You need excavation equipment that works in Martian conditions. You need heating systems to melt ice at temperatures that might be minus 100 degrees Celsius. You need filtration to remove perchlorates and other toxic compounds that are common in Martian soil. And you need to do all of this reliably, day after day, because if your water supply fails, you die of dehydration within days. The same applies to oxygen. You need about 800 grams of oxygen per day to breathe. That doesn't sound like much, but over 18 months, one person needs nearly half a ton of oxygen. Multiply that by a crew of 4, and you're looking at 2 metric tons. Again, too much to bring from Earth for anything other than emergency backup. You need to generate oxygen on Mars. The most promising approach is extracting oxygen from carbon dioxide using a process called solid oxide electrolysis. The Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, that flew on the Perseverance rover demonstrated this technology in 2021 and 2022. It successfully produced oxygen from the Martian atmosphere multiple times, proving the concept works. But MOXIE is tiny, about the size of a car battery, producing maybe 10 grams of oxygen per hour. A full-scale system for keeping humans alive would need to be hundreds of times larger and more robust. What if it breaks? What if Martian dust clogs the filters? What if a component fails and you don't have the right spare parts? These aren't hypothetical concerns. On the ISS, equipment breaks constantly. The difference is that the ISS gets regular resupply missions and, in an emergency, the crew can evacuate. Mars colonists would have neither option. They'd need to fix problems themselves with whatever resources they have available, or die. Food is another enormous challenge. You can bring some food from Earth, freeze-dried and vacuum-sealed, with a shelf life of several years. But for a long-term stay or a permanent colony, you need to grow food locally. Plants are incredibly efficient. They convert carbon dioxide and water into carbohydrates using nothing but sunlight. They also produce oxygen as a byproduct, helping with your life support needs. Growing plants on Mars sounds perfect in theory. In practice, it's nightmarishly difficult. First, you need soil, and Martian regolith isn't soil. It's toxic, filled with perchlorates that would poison you if you ate plants grown in it. You'd need to either wash the perchlorates out or bring soil from Earth or create artificial growing medium. Second, you need lots of light. Mars receives about 43% of the sunlight Earth gets, and Martian dust storms can block sunlight for weeks or months. You'd need powerful artificial lighting, which requires enormous amounts of energy. Third, you need a controlled environment, the right temperature, the right humidity, protection from radiation. You're essentially building a greenhouse inside a pressurized habitat on a frozen desert planet. The movie The Martian made this look almost charming, with Matt Damon growing potatoes in Martian soil fertilized with human waste. The reality would be far more precarious. One failure in temperature control, one breach in the habitat, one contamination event, and you lose your entire crop. And if you lose your crop, you starve. NASA and other space agencies have been experimenting with growing plants in space for decades. The veggie experiment on the ISS has successfully grown lettuce, radishes, and other crops. But these are small-scale demonstrations in a controlled environment with constant oversight from Earth. Scaling this up to feed a crew of humans on Mars with no backup is a monumental challenge. Let's talk about energy, because everything we've discussed, water extraction, oxygen generation, temperature control, growing food, running computers and life support systems, requires energy. Lots of energy. On Earth, we take energy for granted. Flip a switch and the lights come on. On Mars, every watt of power is precious and hard to produce. Solar panels seem like an obvious solution. Mars gets sunlight, and solar technology is mature and reliable. But Mars's greater distance from the Sun means solar panels produce less power than they would on Earth. And Martian dust is a constant problem. During the global dust storm of 2018, the Opportunity rover lost power because its solar panels were covered in dust. The rover never woke up again. For a human habitat, you'd need huge solar arrays and constant maintenance to keep them clean and functional. Nuclear power is the alternative. A small nuclear reactor, something like the kilopower units NASA has been developing, could provide steady power regardless of dust storms or the day-night cycle. But nuclear reactors are heavy, complex, and politically controversial. Launching them from Earth requires special safety measures in case of a launch failure. And on Mars, you'd need people with the expertise to maintain and repair a nuclear power system, which is not a trivial skill set. Either way, your power supply is a single point of failure. Lose power, and everything else fails within hours. Your heating shuts down, and you freeze in the Martian cold. Your oxygen generation stops, and you suffocate. Your water recycling fails, and you dehydrate. Power isn't just a convenience on Mars. It's the thin line between life and death, and it needs to work flawlessly 24 hours a day for years. Now imagine you're an astronaut on Mars, and something goes medically wrong. You develop appendicitis. You break a bone. You have a dental emergency. You develop a kidney stone. On Earth, these are manageable problems. On Mars, any one of them could be fatal. Your crew would include someone with medical training, probably a doctor or paramedic, but they wouldn't have a full hospital's worth of equipment. They'd have what they could fit in the spacecraft, which means diagnostic tools would be limited, surgical supplies would be minimal, and treatment options would be constrained. Could a crew member perform an appendectomy on Mars? Probably, if they had the right training and equipment. But what about more complex problems? What if someone develops a heart arrhythmia? What if someone has an allergic reaction to something unexpected in the Martian environment? What if someone develops depression or psychosis from the isolation and stress? Mental health problems are just as dangerous as physical ones in a confined environment where everyone depends on everyone else. The Soviets and Russians have decades of experience with long-duration spaceflight on Mir and the ISS, and they've documented numerous medical issues, infections, cardiovascular problems, kidney stones, vision changes from intracranial pressure, severe back pain from spinal elongation in microgravity. And that's with the ability to evacuate to Earth if something goes catastrophically wrong. On Mars, there is no evacuation. Medical problems have to be solved on-site or accepted as potentially fatal. There's also the issue of pregnancy, which space agencies avoid discussing, but which becomes inevitable if you're talking about permanent colonization. We have no idea what happens to human pregnancy in reduced gravity or how cosmic radiation affects fetal development. Animal studies suggest serious problems. Mice embryos exposed to microgravity show developmental abnormalities, and radiation exposure during pregnancy increases the risk of birth defects and cancer in offspring. Would a child conceived and born on Mars even be able to survive on Earth? Their bones and muscles would develop in Mars's low gravity. Their cardiovascular system would adapt to Martian conditions. They would be, in a very literal sense, Martian, not human in the way we understand the term. Bringing them to Earth might kill them, just as bringing a deep-sea fish to the surface causes fatal decompression. The first generation born on Mars might be permanently bound to their new world, unable to ever visit the ancestral home of their species. This is both terrifying and awe-inspiring. We could be talking about the beginning of genuine human speciation, the point where Earth humans and Mars humans begin to diverge evolutionarily. It took millions of years for such divergences to occur naturally in Earth's history. We might accomplish it in a few generations through the sheer force of environmental pressure and biological adaptation. Let's talk about the economics, because ultimately, whether Mars missions happen depends not just on technical feasibility, but on whether anyone is willing to pay for them. The Apollo program cost about $280 billion in today's money. It put 12 people on the moon for a few days each. A Mars mission would be far more expensive. Conservative estimates suggest $100 billion to $500 billion for the first mission, depending on the architecture and whether you're planning for return or one-way. Who pays for this? Governments have historically funded space exploration, but government budgets are fickle. Political priorities shift. Public enthusiasm wanes. The Apollo program ended not because we ran out of technical capability, but because we ran out of political will. Congress cut NASA's budget, and the last 3 planned Apollo missions were canceled. The United States hasn't sent humans beyond low Earth orbit since 1972, over 50 years ago. Private companies like SpaceX, Blue Origin, and others have entered the space race with ambitious visions and, in some cases, serious capabilities. SpaceX's Starship, if it achieves its design goals, could potentially make Mars missions dramatically cheaper than traditional approaches. But even Elon Musk, who's perhaps the most optimistic about Mars timelines, talks about needing to reduce the cost to the point where someone could sell their house on Earth and buy passage to Mars. That still implies costs in the hundreds of thousands of dollars per person, multiplied by hundreds or thousands of people if you're talking about actual colonization. And what's the economic return? Mars has no oil, no gold, no easily accessible resources that could be extracted and sold back on Earth at a profit. The transport costs alone would make Martian resources economically worthless in terrestrial markets. Some people talk about Martian mining or manufacturing. But what could Mars possibly produce that would be worth shipping across tens of millions of kilometers of space? The only economically viable products from Mars, at least for the foreseeable future, are knowledge and inspiration. Scientific discoveries, new technologies developed to solve Martian challenges that find applications on Earth, the symbolic value of proving that humanity can become a multi-planetary species. These are real returns, but they're not the kind that show up on a balance sheet in ways that satisfy investors or taxpayers. This suggests that Mars missions, especially one-way missions, would be fundamentally ideological rather than practical. They would happen because people believe they should happen, because we value exploration for its own sake, because we're inspired by the audacity of the attempt. Throughout history, exploration has rarely made economic sense in the short term. Columbus's voyage to the Americas was a financial disaster for its initial backers. The expeditions to Antarctica in the early 20th century bankrupted their organizers. Yet we remember these explorers as heroes, not fools. Perhaps the same will be true of the first Mars settlers. Perhaps they'll be remembered not for any practical benefit they provided, but for their courage, their willingness to sacrifice everything to expand the boundaries of human experience. Or perhaps they'll be forgotten, casualties of an experiment that humanity decides wasn't worth continuing. There's another economic angle worth considering: Mars as a backup for humanity. The argument goes like this: Earth faces existential risks from nuclear war, climate change, asteroid impacts, pandemics, artificial intelligence gone wrong, or other catastrophes we haven't even imagined yet. If all of humanity lives on one planet, a single disaster could end our species. But if we have self-sustaining colonies on other worlds, humanity becomes much harder to extinguish. This is the reasoning behind people like Elon Musk's obsession with Mars. It's not about science or exploration for its own sake. It's about insurance, about ensuring that consciousness and intelligence don't disappear from the universe if something terrible happens to Earth. From this perspective, the cost of Mars colonization, however high, is worth it if it preserves our species. But this logic only works if Mars colonies can actually become self-sustaining, and that's far from guaranteed. For decades, possibly centuries, any Mars settlement would be completely dependent on Earth for complex manufactured goods, for genetic diversity to prevent inbreeding, for cultural and intellectual inputs. If Earth suffered a catastrophe severe enough to threaten human extinction, it would likely also end our ability to support Mars colonies, which would then die out within months or years. True self-sufficiency on Mars would require not just survival, but the ability to manufacture everything from microchips to medical equipment, to maintain genetic diversity in a small population, to develop a stable society under incredibly harsh conditions. We're talking about replicating hundreds of years of industrial and social development in an environment where every mistake is potentially fatal. The timeline for achieving genuine independence might be measured in centuries, if it's possible at all. Let's consider the legal and governmental dimensions, which are surprisingly murky. The Outer Space Treaty of 1967, which most spacefaring nations have signed, establishes that outer space, including the Moon and other celestial bodies, is the common heritage of mankind. No nation can claim sovereignty over Mars. But the treaty was written with the assumption that only governments would go to space. What happens when private companies or individuals establish settlements on Mars? Who has jurisdiction over a Mars colony? What laws apply? If someone commits a crime on Mars, who prosecutes them? If disputes arise between colonists, what legal system resolves them? The Outer Space Treaty doesn't provide clear answers to these questions. Some legal scholars argue that settlers would carry their Earth nationalities with them, subject to the laws of their home countries. Others suggest Mars colonies would need to establish their own legal systems, essentially becoming new nations. The historical parallels are both instructive and troubling. When European powers colonized the Americas, they initially claimed that colonists remained subject to European law. But distance and communication delays made enforcement nearly impossible. Colonies developed their own legal traditions, their own forms of governance, and eventually declared independence. The process was often violent and destructive, particularly for indigenous populations who were displaced, enslaved, or exterminated. Mars has no indigenous population, as far as we know, which eliminates one terrible dimension of Earth's colonial history. But the pattern of colonies becoming independent from their mother countries seems likely to repeat. Mars settlers would quickly realize that Earth, with its communication delays of up to 22 minutes and its physical distance of millions of kilometers, has no practical ability to govern them. They could simply ignore laws and directives they find inconvenient or oppressive. This could lead to conflict. If a Mars colony declares independence, what does Earth do? Send a military force to retake it? The logistics would be absurd, and the cost would be astronomical. Impose economic sanctions? Mars colonies would need to be economically self-sufficient anyway, so sanctions would be ineffective. The reality is that Mars settlements would have de facto independence from the moment they achieve self-sufficiency, regardless of what legal frameworks exist on paper. What kind of society would develop on Mars? This is pure speculation, but the constraints of the Martian environment would likely shape governance in profound ways. In a place where everyone's survival depends on shared life support systems, individualism as we understand it on Earth might not be viable. You can't have someone deciding they don't want to contribute to maintaining the oxygen generators or the water recycling systems. The collective good would necessarily take precedence over individual freedom in ways that would seem authoritarian by Earth standards. At the same time, Mars colonists would be, by definition, exceptional people. They'd be scientists, engineers, pioneers who volunteered for one of the most dangerous and difficult challenges humans have ever attempted. They'd be independent-minded, resourceful, and unlikely to accept arbitrary authority. The tension between the necessity for collective discipline and the pioneer spirit of individualism could produce interesting and unpredictable forms of governance. Some futurists imagine Mars colonies as utopian experiments, places where humanity can start fresh without the baggage of Earth's history and institutions. Others predict dystopia, corporate-controlled settlements where workers are essentially indentured servants, trapped by debt and unable to return to Earth. The reality would likely be somewhere in between, messy and complicated and human in all the best and worst ways. Now let's address something fundamental that we haven't discussed yet: the actual physics of getting to Mars and why it locks you into such constrained timelines. The issue is orbital mechanics, specifically something called the Hohmann transfer orbit. This is the most fuel-efficient way to travel between two planets, and it works like this. You launch from Earth when the planets are aligned in a specific way, then coast for months along an elliptical orbit that intersects Mars's orbit, just as Mars arrives at that point. It's like throwing a football to a receiver running a route. You don't throw where they are, you throw where they're going to be. The beauty of the Hohmann transfer is that once you've accelerated onto the transfer orbit, you don't need to burn fuel for most of the journey. You're just coasting, following the laws of physics as you fall around the Sun. This minimizes fuel requirements, which is crucial when every kilogram of propellant you need to carry requires more propellant to lift it into orbit from Earth. The problem is that Hohmann transfers are slow. The journey to Mars takes 6 to 9 months, depending on the exact alignment, and they're inflexible. Once you're on the transfer orbit, you're committed. You can't speed up or slow down without using enormous amounts of fuel, and the geometry only works during specific launch windows that occur every 26 months when Earth and Mars are properly aligned. There are faster trajectories. You could use more powerful engines and more fuel to take a more direct path, cutting the travel time to 3 or 4 months. But the fuel requirements increase dramatically. You'd need a much larger spacecraft and much more powerful rockets to launch it. The mass ratio, the ratio between your fully fueled spacecraft and your payload, becomes prohibitive. Some advanced propulsion concepts could change this calculus. Nuclear thermal rockets, which use a nuclear reactor to superheat propellant instead of chemical combustion, offer higher efficiency and could reduce travel times. Nuclear electric propulsion, using electric thrusters powered by a nuclear reactor, could be even more efficient for cargo missions, though the thrust is too low for crewed missions with current technology. Fusion drives, if we ever develop working fusion reactors small enough to fit on a spacecraft, could potentially reduce Mars trips to weeks instead of months. But all of these technologies are decades away from practical implementation, if they're achievable at all. For the foreseeable future, any Mars mission will use chemical rockets and Hohmann-like transfers, which means long flight times, narrow launch windows, and all the constraints we've been discussing. There's also the question of what you do during those 6 to 9 months in transit. You can't just put astronauts in stasis pods like in science fiction. They'd need to exercise constantly to minimize muscle and bone loss. Though, as we've discussed, significant deterioration is inevitable. They'd need to monitor and maintain spacecraft systems. They'd need to conduct scientific experiments, if only to justify the mission and keep themselves occupied. And they'd need to live together in a space roughly the size of a small RV for months with the same few people, with no privacy, no fresh air, no escape. The psychological challenges of confinement can't be overstated. The Antarctic research stations I mentioned earlier at least have the comfort of a solid planet beneath them, a breathable atmosphere outside, and the knowledge that they can leave when their rotation ends. Mars-bound astronauts would have none of these comforts. One of the proposed solutions is artificial gravity, generated by spinning the spacecraft. If you rotate a cylindrical habitat around its long axis, centrifugal force creates a sensation of gravity on the inner wall. The faster you spin, or the larger the radius, the stronger the artificial gravity. This could potentially solve the bone and muscle loss problems, maintain cardiovascular health, and provide a more psychologically comfortable environment. But creating artificial gravity adds enormous engineering complexity. Your spacecraft needs to be much larger to have a radius sufficient for comfortable rotation without excessive Coriolis forces that make movement difficult and nauseating. You need a robust rotation mechanism that can spin for months without failure. You need to design all your systems to work in a rotating reference frame. And you need more fuel to launch this larger, heavier spacecraft. NASA and other space agencies have studied artificial gravity concepts for decades, but no crewed spacecraft has ever implemented it. The technical challenges and cost have always been deemed too high compared to simply accepting the physiological consequences of microgravity. For Mars missions, that calculation might change, but we're still talking about technology that hasn't been proven in practice. Let's talk about something more abstract, but equally important: the philosophy of risk in human spaceflight. How much risk is acceptable? When the Space Shuttle program ended, it had lost 2 orbiters and 14 astronauts out of 135 missions, a failure rate of about 1.5%. That's a 1 in 67 chance of dying, which is extraordinarily high by modern standards. No airline could operate with those statistics. Yet astronauts continued to volunteer, knowing the risks. Mars missions would be far riskier than shuttle flights. There are so many potential failure modes, so many things that could go wrong, so many variables we can't fully predict or control. Realistic estimates of the probability of crew loss on the first Mars missions range from 10% to as high as 50%. Would we, as a society, accept sending people on a mission with a 1 in 2 chance of death? Different cultures and different eras have different risk tolerances. The early days of aviation saw frequent fatal accidents that would be unthinkable today. The first attempts to climb Mount Everest had casualty rates that would shut down any modern expedition. We've become more risk-averse as societies have become wealthier and technology has improved. Yet, space exploration, by its nature, will always carry significant risk. There's a philosophical question embedded here. Do we have the right to prevent people from taking risks if they fully understand and accept them? If someone wants to volunteer for a one-way Mars mission with full knowledge that they might not survive, that they'll never return to Earth, that they'll face hardships we can barely imagine, should we stop them? Or is it their right as autonomous individuals to make that choice? The counter-argument is that space missions aren't purely individual decisions. They involve enormous public or private resources. A failure could set back space exploration by decades, just as the Challenger and Columbia disasters temporarily grounded the shuttle program. And there's something about watching people die in space, broadcast around the world, that traumatizes societies in ways that other dangers don't. We have an emotional investment in astronauts that we don't have in, say, deep-sea divers or mountaineers, even though those activities can be just as dangerous. This brings us to an uncomfortable truth about the one-way trip concept. It might actually happen whether we plan for it or not. Imagine a round-trip Mars mission where something goes wrong. The return vehicle fails. The fuel production doesn't work. A critical component breaks. Suddenly, the astronauts are stranded. They can't come home. Do they give up and wait to die? Or do they adapt, salvage what they can, extend their supplies, and try to build a life on Mars for whatever time they have left? History suggests they'd choose survival. Human beings are remarkably resilient and creative when faced with death. The stranded astronauts would become the first permanent Mars colonists, not by choice, but by necessity. And if Earth continues to send supplies, if the mission evolves from rescue these people to support the first Mars colony, then the one-way mission would have happened organically, growing out of failure rather than design. In some ways, this might be the most realistic path to Mars colonization. Not a grand plan executed flawlessly, but a series of missions, some successful and some failing, gradually building up infrastructure and knowledge until permanent habitation becomes inevitable. It's messy and unplanned, and involves accepting casualties along the way. But it's how most human exploration has actually worked throughout history. Consider the settlement of Antarctica in the early 20th century. Multiple expeditions failed catastrophically. Robert Falcon Scott and his entire team died returning from the South Pole. Ernest Shackleton's endurance was crushed by ice, stranding his crew for months. These failures didn't stop Antarctic exploration. They informed it. We learned from each disaster, improved equipment and techniques, and eventually established permanent research stations on the continent. The same pattern would likely play out on Mars, except the stakes are higher and the environment is more unforgiving. There's also the generational aspect to consider. The people who first go to Mars will be pioneers, taking enormous risks for the sake of expanding human knowledge and presence in the solar system. But what about their children, if they have any? Those children won't have chosen Mars. They'll be born into an environment where they are trapped, unable to ever visit Earth due to the physiological adaptations we've discussed. Is it ethical to create people who are bound to Mars from birth, who have no choice in the matter? On Earth, children don't choose where they're born either. A child born in a war zone or in extreme poverty didn't choose those circumstances, yet we don't consider their birth unethical. Location and circumstance are always accidents of birth. But there's something qualitatively different about being born on a planet you can never leave. In an artificial habitat where equipment failure means death, where the outside environment is instantly lethal. It feels like imposing a burden that goes beyond normal parental responsibility. Yet if Mars colonization is going to succeed, there must be subsequent generations. A colony composed only of the original settlers would die out within decades. You need children, families, a growing population that eventually becomes self-sustaining. This means accepting that some humans will live their entire lives on Mars, perhaps never even seeing Earth except as a bright star in the Martian sky. What would it be like to grow up knowing Earth only as an abstraction? Your parents might tell you stories about rain, about forests, about oceans, about breathing air without a mask, but you'd never experience any of it. Earth would be mythical, like Atlantis or Valhalla, a paradise that exists only in stories. Would you resent your parents for condemning you to Mars, or would Mars be all you know, your home in a way Earth never could be? Science fiction has explored these themes extensively. Kim Stanley Robinson's Mars trilogy imagines multiple generations of Martian settlers developing their own culture, their own identity, distinct from and eventually in conflict with Earth. Robert Heinlein's stories depict colonists who see themselves as Martians first, human second. These narratives recognize that culture and identity are shaped by environment, and the Martian environment would shape its inhabitants in profound ways. Language would evolve differently on Mars. New words would emerge for Martian phenomena that have no Earth equivalent. Idioms and expressions would reflect Martian experience rather than Earth's. Imagine Martians using phrases like clear as Olympus Mons or colder than a polar crater that would be meaningless to Earth humans. Within a few generations, Martian English or Martian Mandarin or whatever languages the colonists speak would diverge noticeably from their Earth counterparts. Cultural practices would adapt to Martian realities. Holidays and celebrations tied to Earth's seasons would lose meaning on a planet with a different calendar and different seasonal patterns. New traditions would emerge, commemorating the first landing, celebrating successful harvests from Martian greenhouses, marking the Martian year, which is nearly twice as long as Earth's. Religion might evolve in interesting ways as colonists grapple with their isolation and the fundamental questions of meaning and purpose in such an alien environment. Social structures would necessarily be different. In a small colony where everyone's survival depends on everyone else, individualism would compete with collectivism in complex ways. Privacy would be a luxury, possibly non-existent in the early years. Relationships, romantic and otherwise, would develop in a pressure cooker environment with limited choices. The gene pool would be dangerously small, requiring careful genetic management to prevent inbreeding, possibly including genetic material shipped from Earth or extensive use of reproductive technology. Economic systems on Mars would bear little resemblance to Earth capitalism. Money might be meaningless in a colony where resources are centrally managed and distributed based on need rather than market forces. Work would be organized around necessity rather than profit. Everyone would need to contribute to survival tasks, from maintaining life support to growing food to repairing equipment. The division between intellectual and manual labor that characterizes Earth societies might collapse on Mars, where the physicist might also need to know how to fix a water recycler and the engineer might need to help harvest crops. Let's return to the central question that frames all of this. Why is Mars functionally a one-way trip? We've explored the technical reasons, the enormous fuel requirements for return, the physiological damage that makes astronauts unable to safely return to Earth, the narrow launch windows and long transit times that make rescue impossible. We've examined the economic reasons, the prohibitive cost of round-trip missions compared to one-way colonization. We've considered the philosophical and ethical dimensions, the nature of exploration, the acceptable levels of risk, the rights and responsibilities of pioneers. But perhaps the deepest reason Mars is a one-way trip is psychological and existential. Once you've left Earth, once you've spent years adapting to Martian conditions, once you've built a life and a community on another world, what does returning even mean? You wouldn't be going back to the life you left. That life no longer exists. Everyone you knew has moved on. Earth has changed in your absence. And you've changed too, fundamentally, in ways that would make readjustment difficult or impossible. The explorer who returns from Antarctica or the Amazon rainforest comes back changed, carrying experiences and perspectives that set them apart from those who stayed home. But they can still communicate, still reconnect, still reintegrate into society. The Mars colonist would face a gap too wide to bridge. They would be, in the most profound sense, alien to Earth, and Earth would be alien to them. The return journey, even if technically possible, might be a return in body only, not in spirit or identity. This is why some advocates argue we should embrace the one-way nature of Mars missions rather than pretending they're round trips. Be honest about what we're doing. Select people who understand they're leaving forever. Design missions for permanent habitation rather than temporary visits. Build the infrastructure for long-term survival rather than short-term exploration. Except that we're not sending astronauts. We're sending colonists. And the distinction matters. The critics of this approach argue that it's unnecessarily fatalistic, that we should always plan for return, Always give people options. Always maintain hope. They point out that technology improves, that what seems impossible today might be routine tomorrow, and that closing the door on return eliminates future possibilities. They worry about the message it sends, that we're willing to abandon people on Mars, to write them off as acceptable losses in the grand project of colonization. Both perspectives have merit. The tension between them reflects deeper disagreements about the nature and purpose of space exploration. Are we exploring for science to answer questions about the universe? Are we expanding for survival, to ensure humanity persists if Earth becomes uninhabitable? Are we driven by an innate need to explore, to see what's over the horizon, regardless of practical benefit? Or is it some combination of all these motivations, impossible to untangle and perhaps unnecessary to parse? What's clear is that Mars represents a threshold in human history. Every previous human migration, even the most dangerous, has been within Earth's biosphere. The Polynesians who sailed across the Pacific, the humans who crossed the Bering Land Bridge into the Americas, the explorers who reached Antarctica, all of them remained on Earth, breathing Earth's air, subject to Earth's gravity, capable of growing Earth food and drinking Earth water. Mars is different. It's truly alien, requiring artificial systems to keep us alive every moment we're there. Crossing this threshold, establishing permanent human presence beyond Earth, would mark a fundamental shift in what it means to be human. We would no longer be a single-planet species. Our story would no longer be confined to one world. The descendants of Mars colonists, if they survive and thrive, might look back on Earth the way we look back on the African savanna where our species evolved, as the origin point, important historically but no longer home. Is that future worth the cost? Worth the risk? Worth the lives that will certainly be lost in the attempt? There's no objective answer to these questions. They're matters of values, of vision, of what we believe humanity's purpose and potential to be. Some people look at Mars and see a frozen hell, a place of death that we have no business trying to inhabit. Others see opportunity, challenge, the next chapter in the human story. What's undeniable is that if we go to Mars, when we go to Mars, if current trends continue, it will be a one-way trip in every sense that matters. The astronauts who make that journey will leave Earth behind, not just physically, but existentially. They will become something new. Martians, the first members of a branch of humanity adapted to a world that has never known life. They will face challenges we can barely imagine and hardships we can only simulate imperfectly. Some of them will die. All of them will be changed, and yet I have no doubt that when the call goes out for volunteers, thousands of people will apply. Because for all our talk of risk and danger and difficulty, there's something in the human spirit that refuses to be confined, that looks at the impossible and says, "Let's try anyway." That spirit has taken us from caves to cities, from walking to flying, from Earth to the Moon. Now it's pulling us toward Mars, toward the next impossible challenge. The journey to Mars is a one-way trip. But perhaps that's not a flaw in the plan. Perhaps that's the point. Perhaps leaving everything behind, risking everything, committing completely to an uncertain future on an alien world. Perhaps that's what exploration actually means. Not tourism, not a visit, but a permanent leap into the unknown from which there is no retreat, only forward into whatever future we can build with our own hands. The first footprints on Mars will last for millions of years, undisturbed by wind or rain in the thin, dry atmosphere. They'll mark not just where humans walked, but where we chose to stay, where we decided that one world was no longer enough, where we became truly a species of explorers, reaching out into the cosmos, one irreversible step at a time. But why would a Mars colony collapse within months? The video on the screen explores that. While headlines shout about sending people to Mars and building the first permanent Mars colony, the real truth is almost never discussed. In this in-depth documentary, we reveal the harsh scientific and engineering realities that make a Mars colony destined to fail, possibly within just months of landing.